So today we will cover the second part of optimal power flow. Last week we saw parts of the optimal power flow problem that are very specific to the modeling of a grid. What we will see today is a bit less specific, but is practically always present when we do an optimal power flow. It has to do with management of uncertainty. So this is the topic for today. The tools and the techniques we will see today and next week are very generic. They apply to more general control problems than just smart grid, but they are very present and very important in the context of smart grid. We will start by a small chapter that I call Quantifiers in Constraints. So this is a technical excursion we will need to do in order to be comfortable with its application to the smart grid context. So let's start. We consider the following optimization problem. Lost. Yep. Here I'm writing a toy optimization problem, but we need to analyze it in detail. So it's a minimization problem with two optimization variables, U1, U2, some objective functions, some constraints, that's the classical thing. And here there is one constraint that has a quantifier. The quantifier says for any D1 such that D1 is between 4 and 5, and this relation, U1 plus 2, U2 minus 3, D1 is less than 10. So implicit here is that D1 is a real number. So and of course, this is not something that is easy to handle like we had before. We had perhaps a quantifier before when we had for every index j, which means we had a finite number of constraints. Here we have an infinite number of constraints for any possible value of d1 in this interval, such that a constraint that binds together the control and d1, the optimization variable u1, u2, and this supplementary variable d1 is satisfied. In this context, d1 is called a disturbance, and it typically represents uncertainty. So it is not an optimization variable in the sense it is not something that we can act upon. We can think of it as a value that is given by external forces, by nature, if you want. So we need to choose two parameters, u1 and u2, that satisfy a constraint that is in some sense not totally known. Few comments on this. Here the optimization variable is u1, u2, not u1, u2, d1. So d1 appears in the constraint, but with a quantifier. So it is what we can call a dummy variable. Dummy variable means a variable that we can call any way we want, and that is not in particular an optimization variable. We're not interested in finding an optimal value of d1. It is more something external, a disturbance here. And as we can imagine, we're interested in finding values of u1, u2 that maximize this subject to the constraints we have here. So that's the first form of problems. Here is a little one where you can exercise your understanding. Here, I'm giving two possible ways to get out of those constraints. My goal here is to get rid of D1. I propose two solutions here, which, if any of those, are correct answers. Speak Up is reopening the room. Murphy's Law today. Okay, I will not be able to get your feedback because my Speak Up here is hanging. Let me try to connect to another network. Here we are. Now you should see in the speak up room the poll that is finally open. I close the poll in a few seconds. And the correct answer is both. Both here. But the most important thing is the first one. So saying that this quantity U1 plus 2U2 minus 3D1 is less than 10 is the same as saying U1 plus 2U2 is less than 10 plus 3D1. Let me write this. Right. And in general, saying that an expression is less than f of D1 for all D1 that belong in some set, as long as the expression does not contain the letter D1, then it's the same as saying that this expression is less than the minimum of this. So we find a link between a constraint with an optimizer and the solution of an auxiliary optimization problem here. So this is exactly what we have here. Our constraint is equivalent to saying that U1 plus 2U2 is less than the minimum of the right-hand side. So A is perfectly correct. Now, this is an optimization problem in one single variable, so it's probably easy to solve. What's the minimum of this? When D1 is between 4 and 5, this is an increasing function of D1, so the minimum is when D1 is as small as possible, which is 4. 3 times 4 gives plus 10 gives 22, so B is simply the solution of 1. So that's the first take-home message. Constraints of these types are solved by solving an auxiliary optimization problem, one per constraint, which is what we did here. Here is another type of problem with a quantifier in constraint. Problem P2 is very similar, except it means there exists D1. So we look for U1 and U2 such that it is possible to find one D1 that satisfies this constraint. So the interpretation is a bit different. We're not saying that we play against an adversary, against nature, and we don't know what the adversary will play. Here it's more the cooperative scenario, where I say, I want to play U1, U2, such that it is possible for someone else to play D1 that will satisfy the constraint here. Other than that, the comments are the same. Again, the optimization variable is U1, U2. D1 is a nuisance variable, a dummy variable, one that is added to my problem in the constraints, but not the one that defines the optimization problem variables here. Let's continue with a similar quip as a minute ago. If we now replace the constraint by there exists instead of for all, what becomes the solution of this removal of the quantifier in the constraints? I close the poll in a few seconds. And the majority says C, which is indeed the correct statement. for the same reason as before, except now when we say there exists a D such that, that means U1 plus U2 is less than a quantity, than the value of this quantity for one of those things. So saying that an expression is less than f of D1 for at least one is the same as saying it's less than the max. So that's simple but important. So here it means we can simply get rid of the constraint by expressing an optimization problem, which is the max here. And here what I've done is simply to solve this optimization problem, and we find 25. So if we think of what we've just done, we had an optimization problems where there appeared to be a variable D1, but in fact, when we analyze carefully the constraints, we see that we are left with a constraint where D1 does not appear, which is what is really happening. Here is a little variant where we have a classical problem where there is no quantifier in the constraints. So D1 appears, but there is no quantifier. That means D1 is an optimization variable. So I might care about minimizing the same objective functions as before, the same constraints, except now I impose the constraint on D1. The optimization variable is U1, U2, D1. What does it mean concretely from a modeling viewpoint, from an engineer's viewpoint? Here it means that I have to choose D1. I have to choose U1 and U2 and D1. So it's not a game with two partners. It's a single partner event where I have to choose U1, U2, and D1. And all the constraints are up to me to satisfy. In some sense, there is no uncertainty in this problem here. For example, here I have a problem P3, the problem we just saw. I could solve it by, if phi is a well-behaved function, for example, if phi is convex, or even better, linear, then that will be something easy to solve if the constraints in C are also convex. If I can solve P3, is it solving P2 or P1 or both? Think about it. I'll close the poll in a few seconds. And there is a tie between answer B and C. The correct answer is B. If you think about it, that should be almost obvious. In P3, we're saying I have to choose U1, U2, and also D1 that satisfies this. In P2, I'm saying I have to choose U1 and U2 such that someone else could choose D1 that satisfies the constraint. Well, if someone else can choose D1, I can choose it as well. So if there exists a D1, then I can find one. And vice versa, if I can find one, then there exists one. So P2 and P3 are in fact the same. Not exactly the same, because in P1, I'm not interested in D1, whereas in P3, I am. But apart from that, technically, solving one or solving the other, both are the same. In contrast, in P1, that's very different. In P1, I cannot choose D1. I have to choose U1 and U2, and someone who is truly an adversary, who is not cooperating with me, will choose D1. The only thing I know is the bounds that this guy might choose. But I don't know what will be chosen. So I have to satisfy the constraints regardless of what the adversary will choose. So that's a very different thing. I cannot choose D2, D1 here, and therefore it's not the same as adding it as an optimization variable. So that's perhaps the take-home message. It's not so complicated, but it's very important. In particular, I call these supplementary variables and constraints. Solving a problem that has a quantifier, there exists a D subject to some additional constraints on D, which I formulate by saying D is in the set capital D. Also some constraints that may relate U and D, U my optimization variables, other constraints on U. This is the same as adding D as an optimization variable and removing the quantifier. What exactly it means is given here, which is what we saw before. The optimal values of both are equal. If I can solve problem A, that means there exists a D star, and this D star added to my optimal solution of A is an optimal solution of B, and vice versa. If somebody can solve B, then we can solve A, for the reason I've given a minute ago. The formal proof is given in the slides, but it's only if you want to check that formally. The intuition is perhaps more important. So in summary, for this preparation phase, we have seen that if in constraints we have a quantifier that's truly adversarial with a for all, then this is equivalent to saying that the expression is less than the worst case, and the worst case is the minimum in this case. In contrast, if the condition is that there exists something, then it's equivalent to the expression being less than the best case, which is the maximum. In both cases, we replace the constraint with a quantifier by a constraint by solving an optimization problem, if we can. And another thing, if we have a quantifier which is there exists, we can get rid of it either in this way or in that way by simply adding the D as an optimization variable. Both ways are possible, and we will see in a few more moments how we can use those two directions to make something useful. Recap. Here is a problem that should look familiar. This is the kind of problems we have been having. Here, I'm trying to compute an optimal set point for the generators and for the loads. Which problems can be used to solve P? I'm proposing A and B. Which do you think is a correct answer? I close the poll. And the answer is, of course, A. So try again. The answer is A. A is, in fact, not the problem we should be really interested in. In A, we control the generator set point such that there exists a load, which is probably not the real thing we're interested in. As we will see in a minute, we're interested in minimizing the cost of generation subject to all possible values of the consumptions of the loads for which we have a forecast. But now the forecast is not given by a point forecast by a single value, but an interval. So B is probably the true problem we have. P is not solving B, P is solving A by adding the variables here. So take home message, well, when we have uncertainty about some of the parameters, it is not the same as adding variables to the optimization problem. We must do something else. If we do what we just discussed in a general context, we can obtain a recipe, a method, to solve a complete set of a whole class of problems. Those are called robust problems. Robust problems are problems where we need to minimize a cost function subject over an optimization variable, u, subject to constraints on u, and constraints on u and d, which is a disturbance. So the constraints take the form we had before. Some expression is less than some maximum quantity for all d. The d must satisfy a number of things here. And in this case, I'm assuming that the joint constraint on u and b is linear. It's linear in u and linear in b. In this case, we can solve this once for all by using exactly what we've done on the toy examples. I look at one of these constraints, this one here, and I'm saying this must be true for all d. Then it's the same as saying that I put all the u on one side and all the d on the other. It means the left-hand side is less than the value of the right-hand side for all d, which, as we've discussed, is the same as saying it's less than the minimum, which is the worst case here. So we have to solve an optimization problem, find the minimum of this quantity subject to those constraints. So there are linear constraints on the disturbance d. D is typically a vector, not a single number like we had before. D has p dimensions, and the objective is linear. So we have to solve a linear program, one per inequality constraint here. I call hj the optimal value of this optimization problem, and then we can simply replace the robust constraint by a traditional constraint, which is just one linear constraint on u. So recap, if I have to solve an optimization problem that falls in this form, there is a disturbance, an adversarial disturbance that I cannot control. So there is the for all quantifier. If the combination, if the constraint is linear in both, then for every constraint, I have to solve one linear problem, and then I replace the constraint by a traditional constraint obtained from the optimal value of the linear problem. Voila. So this is what we needed to be able to continue our grid control problem. So our grid control problem, if you remember, we had a small grid, high voltage or medium voltage grid with 3 generators, one being the slack bus here, and we have loads. And we had found optimal values for given values of the costs of generation and given constraints on the lines using the DC approximation. So here we'll stay with the DC approximation. But now assume that the loads are not known exactly, but are known with some uncertainty. Is that realistic? For loads, yes. Depending, of course, on the size of your grid. If you have a very large grid at the size of a big country like France or Germany, then it is possible to have a very, very accurate prediction of the load, less than 1% of accuracy. So we would have much smaller interval here. If your grid is smaller, of course, the law of large number doesn't play for you, so the prediction interval will be smaller. The loads may be pure consumption, or they can be net loads. That means consumption minus local generation, typically solar power. So solar power typically introduces a bit more of uncertainty because there are clouds that even if the weather forecasts say it will be nice weather, they can be a bit less than what was forecast, or a bit more if there are fewer clouds than anticipated. Here I'm assuming there's this amount of uncertainty, around 10% on L1, L2, and a bit less on L3. So based on a forecasting exercise, this is what I thought would happen. So this affects the dispatch plan in the sense that now I need to consider the load quantities that are written in blue here as disturbances. They are not known in advance here. So we have seen how to address the constraints that are the presence of disturbance in the constraints, but there are other things we need to discuss. So observe that we need only to control G2 and G3 because bus 1 is a slack bus. So G1 will be a result of two things, of what we have chosen and what nature has chosen here. So it will be given by the algebraic sum of all this here. Therefore, the cost that we have is not entirely in our hand. The cost is a result of our control actions, G2, G3, but also the emerging value of G1 that depends on the disturbance here. So we have a small problem here. We cannot simply cast the problem as it is given here by saying, I want to minimize the cost, because in an optimization problem, the cost should be a function of the things that you can play upon here. So we need to decide and reason about what the cost should be here. What should we minimize here? A very classical approach, which is not the easiest one, but is very often found in the literature, is to take as cost some kind of average. So to make sense of that, we must imagine that there is a stochastic modeling of the disturbance here. So to recap here, we have to choose some control parameter, our generations, nature or an adversary, we choose some random disturbance, and the system state. In our case, the state is all the variables that the DC approximation will need, the theta, the branch powers, but also the slack bus power. All the system state is a result of our choice and of the disturbance. However, so we don't know what it will be, but we know the function that is used to generate the state from the value of the control and the disturbance. So the cost itself is random if we assume that the disturbance is random. One very classical approach is to get rid of this randomness by taking the expected cost. Expected cost, that means we compute a value C bar of U, which is in average what we would expect to pay for if we choose U and if nature chooses whatever nature wants, assuming there is a distribution we can put on the parameter D here. So that's one step, and that step allows us to get rid in the objective function of the embarrassing D, which is not control. So this is called stochastic optimization, or also called average cost optimization. Let's do this for our DC OPF. Here, we have to compute what is the average, the expected cost when nature plays L1, L2, L3. What do we know about nature? Well, we don't know much. We know the confidence intervals for the prediction here. So one possible way to go further is to find a distribution here. We need to assume a way to compute the average value. Here we could assume, for example, L1 is uniform between those two values. Perhaps not the most reasonable thing, but that's one way that can be defended. If we know nothing about a random variable other than it's an interval in which it plays, then the less informative, the most general distribution is the uniform distribution on this interval. So we could take this, and then I need to compute what is the expected cost of generation given this assumption. Here, there's a number of technical problems. The first step is to simplify my writing by eliminate all the variables that are not necessary. For example, the branch power flow here, Pij, are given by those simple equations. So instead of keeping them as optimization variable, I pre-process my thing and I reduce a number of variables. So I have G2, G3, my control, G1, theta 2, and theta 3 that are the state here. I'm not yet done because I need to compute the average cost, which is the average over all values of the state, which is now itself random, when the disturbance takes this average value. So one way to go further is to eliminate the state at all by saying that the cost is a function of U and of F of U and D, because the state is a function of my control and D. So my state here is G1 theta 2 theta 3. What is the state as a function of my control and the disturbance. Well, here it's not so complicated. With the DC approximation, the disturbance is the value of the loads. My control is the value of these generations, and by the DC power flow equation, then we know that G1 will be L1 plus L2 plus L3 minus G2 minus G3. So this will be true for every value. Now, if I take the expectation, then it will be true also in expectation if C1 is because C1 is a simple coefficient, is a linear function. So it will be C1 multiplied by the average here, which if I expand will give C2 minus C1 G2 plus C3 minus C1 G3 plus 7 C1 here. So this is a constant term. We don't care about it to find the optimal set points. So we have now obtained the average cost as a linear function of G2 and G3. This was our major step to achieve. The constraints, here they are. We see that the constraints contain the control, G2, G3, state, G1, and the thetas here. Here too, it is easier if we express the constraints in terms of only the control and the disturbance, which I do here. It means I eliminate G1, theta 2, and theta 3, which is easy to do in the DC approximation because everything is linear. So I obtain G1, theta 2, and theta 3 by simply solving linear systems as a function of only G2, G3, and the disturbance here. I plug this into the constraints, and I obtain that kind of things. This is the problem I have. This is the objective function, which depends only on my control, which is the expected cost. So we've removed the disturbance from the cost, but of course it is still present in the constraint, and we have to formulate that for every value of the disturbance that are in those intervals, those inequalities must be true here. Now the good news is that this fits exactly in the form we have seen before. We have to minimize a function of u subject to constraints that are linear and u and the disturbance. And the constraints on the disturbance themselves are linear. Here they are simple, but they are also a special case of linear constraints on the disturbance here. So we can solve it using what we have just seen a minute ago. So we have to solve an optimization problem Q1 here. For example, if I look at one of the constraints here, G1, this one here. So this constraint comes from this value here, right? So this constraint here, because G min is 0, gives us this inequality, which has to be true for every L1, L2, and L3. In this case, it's fairly easy. We don't even need the theory I just made an hour ago. We need to take what is the worst case of this. Well, the worst case is when this sum is minimum, and the minimum is obtained by taking the minimum values of all the L's, which gives us a value of this optimum right-hand side here of 6.6. So this robust constraint simply means that G2 plus G3 is less than 6.6, which is the maximum generation I can have when the loads are minimum. Here, however, it's very atypical. It's a case where I could solve the robust constraints. I could de-robustify the robust constraint manually by simple inspection, by saying the worst case is easy to find. In general, of course, this is not what happens, and we will need to solve a linear problem here. So if we do that, for each of the constraints, this is what we obtain here. We obtain constraints on G2, G3 that are given by the values here. Notice that I've found a number of constraints. Every unequal sign here is one constraint here. So I had a number of auxiliary optimization problems to solve here. Interesting here, what happens if I increase the uncertainty? Here the uncertainty was plus or minus 10 on this load, for example. If I multiply it by 5, a bit more. And similarly for the other constraint here. So I can redo the same exercise, which is not very difficult. And here are the constraints I obtain. Then if you look carefully at the first two inequalities, you see that they are inconsistent. So that's an example of an optimization problem that is unfeasible. The set of constraints has no solution. There is no value of G2, G3 that satisfies all the constraints here. Well, this is embarrassing, but this is something to be aware of. If we make a robust problem too robust, if the uncertainty is very, very large, there can be no solution. So here, there is no fixed value of the set points G2, G3 that is able to cope with such an uncertainty here. So that's our first take-home message. We will see in a few more moments that we can improve our control by putting a controller into the loop. And we will see that with a simple linear controller, we can extend the range with which we can work. But here, with a fixed control that is robust, there is a limit to what we can do, which of course is expected. Robustness has a cost. If you want to organize a system, if you want to choose a set point for something, in the face of uncertainty, then it will cost you something here. And in the worst case here, it will cost you infeasibility. We see here in the value of the optimal expected cost as a function of the uncertainty. The first case we studied was the uncertainty on the last load was 20. And I said, if I increase it up to more than 100, then it doesn't work. But up to 100, it works. However, the cost increases here. So that's the second take-home message. Uncertainty costs something, right? There is a methodological bug that you often find in literature or in news where people say, if I had done this, it would have been much better. So if I had set my generation to those values, I would have reduced my cost. But that's an exercise you do after the fact. If you do it after the fact, it's always easy to say, what would have been the optimal choice to do if I had known all the disturbances? But that's not how the equation is posed. You have to take a decision in the front of uncertainty, and this uncertainty will cost you something. So that's an important thing to remember. I've seen a very simple example where I assume that the cost was linear. And when the cost is linear, then we don't need to worry too much about the distribution of the disturbance, because the only thing that appeared in the computation was the expected value of this disturbance, the average value here. Let's look at another example where the cost is quadratic. So why would a cost be quadratic? Well, some generators, thermal generators, for example, typically have a quadratic cost. So the fuel they burn doesn't depend linearly on the power they generate here. It's a more complicated function generally, but here let's take this simple function. So I redo the same exercise as before, but I assume the cost of every generator is quadratic here. Now I need to compute the expected cost. To simplify here the discussion, or not to simplify it, but to make it more aligned to what we will often see in practice, I am assuming that the unknown quantity, the disturbance, follows a Gaussian distribution. So N stands for normal. So a normal, or which for me is a synonym of Gaussian distribution, with mean Li, with a bar, stands for the mean, and some variance here. A minute ago, I was assuming it's uniform. So uniform is a much nicer distribution in some sense. Here, to make things a bit worse and more classical, I assume Gaussian. So now we have a more tricky problem. We need to compute what is the expectation of the cost here. So the cost is given here. It's the cost of G2, G3. So remember, C2, G2 means simply C2 multiplied by means now gamma G2 to the square here. The tricky part is the cost of G1. Now G1, by our DC approximation, is the sum of the loads minus G2, G3. And I have to take the expectation of that. Well, the important thing to be able to compute the expectation is to have a clear idea about what we are doing. What we are doing here is we are treating G2 and G3 as fixed, even though they are not fixed because we want to find their optimal value. But in the computation of the expectation, they are fixed. Remember the game. I choose G2, G3. Nature chooses L1, L2, L3. And the question I'm asking is, what in average should I pay for as a result of my choice of G2, G3? So the random thing is L1, L2, L3. So we have to compute the expectation of, I factor out gamma that goes out of everything. It's the expectation of this first term to the square, and then the others are non-random. So they are simply equal to G2 square plus G3 square. And the question is, what is this expectation? So I can view this as a random variable, minus G2 minus G3 plus L1 plus L2 plus L3, which has a mean, which is equal to the constant plus the sum of the means of the constituent random variables. This random variable is a linear combination of independent Gaussian random variables. I did not mention it, I should have mentioned it. Here I assume that the loads or the uncertainty about the loads are independent. Something that is sometimes a good idea, sometimes a bad idea. That's another topic. Here I'm assuming they are independent. So if I sum three independent random variables that are Gaussian, I obtain also a Gaussian random variable. And the mean is the sum of the mean, and the variance is the sum of the variances. So the variance of L1 plus L2 plus L3 plus a constant is not modified by the constant. So it's the variance of L1 plus L2 plus L3, which is the sum of the three variances here. So this is a random variable with mean this and variance the sum of the variances. And this is the expectation of the square. Now there's a little mathematical probability formula that says the expectation of the square of a random variable is equal to the mean to the square plus the variance. In fact, if you think about it, that's the definition of the variance of a random variable. To make a long story short, the expectation of this to the square is the mean to the square plus the variance. So we see that at the end, the cost is given by this formula. It is quadratic in G2, G3 through this term here, plus constant terms, plus the G squares here. We see that, again, there is a cost to pay for uncertainty. We see that the average cost is larger when the variance of the disturbances is larger, which is expected here. So we have here a quadratic thing to solve that we will let MATLAB hopefully solve for us. Here, however, we have another problem. We cannot put deterministic bounds on the L1, L2, L3 because if we take it strictly, Gaussian random variable can take any value from minus infinity to plus infinity, which is impossible here. The load cannot be arbitrarily large. It cannot be minus 10 gigawatt, which would mean you have local generation that is huge, and it cannot be immensely positive either. So the Gaussian distribution is a very simplified view of things. However, in practice, the Gaussian distribution also decays very, very quickly. So, for example, the probability that the standard Gaussian variable, one that has a variance of 1, is larger than plus or minus 196 is 5% here. So if you accept a probability of failure, so that's something we have to realize when we have stochastic optimization, usually we will need to accept some probability of failure because it will be mathematically impossible to guarantee that the constraints are always valid. Shouldn't worry us. Anyhow, the probability distribution we're putting on the uncertain things are probably not very exact either, so we have to live with them. Here, for example, in a grid, the probability of failure is usually very, very small. Here, I took it equal to 10 to the minus 4. So I accept that my dispatch plan doesn't work with a probability of 10 to the minus 4, which is one of the standard numbers we often find in power grids here. So if I take this value, I have to redo this exercise here. I look into MATLAB or in tables of Gaussian distribution. What should be the thresholds that I accept, such eta, such that the probability of exceeding the threshold for the sum of those things is less than this quantity. And then we find that we obtain here 3 to 30, we find eta equal to 4. So roughly speaking, we have to take the square root of the variance, which is the standard deviation, plus or minus a factor of 4. What did we do here? We replaced something stochastic into something that looks familiar now, a robust optimization problem. We have here said that the constraints should be true for every value of L1, but the L1s that I have are between bounds here. Those bounds might be a bit painful to compute, but once they are computed, they are fixed here. They don't depend on my choice of optimization variables, nor on the disturbance, the specific value of the disturbance. So we are back to a problem of the nature we had seen before. So, take-home message. In stochastic optimization, we have to choose control, and nature will choose disturbance. And the result of that, the state, will depend on both my control and the disturbance here. And in the context of grid, the disturbance are the things truly given by nature, like renewables, or more exactly, the forecast error of renewables, and similarly, the forecast errors of the loads, which is more by humans more than nature. Then we want to minimize the expected cost, subject to constraints that are made in the form of robust inequalities. And if we're able to linearize them, then we will have a problem that we know how to solve by now. So this change of the constraints from something probabilistic to something determinist is called chance constraints here. So we have constraints that are true with some probability. Voilà. Assume we do this for this problem. How many auxiliary problems will we need to solve? I close the poll. And the majority says C, but the correct answer is D. We have to look at the robust constraints. So the robust constraints are the constraints that involve, there is the for all quantifier, and those are the constraints that involves both my control and the disturbance. So how many unequal signs do we have? We have 1, 2, plus another line here, 1, 2, 3, 4 lines with 2 inequalities at every line. So we have 8 constraints. So if we apply the method I've shown here, we will need to solve 8 auxiliary problems, which, by the way, it's simpler to solve 8 small problems than to add all those variables to the problem like we might be tempted to. Voilà, time for a break. It's 10 past 10, so we resume in 10 minutes at 20 past 10.